here. So I'm going to begin with what I call the energetic information theory since yesterday. Then I'm going to talk about the efficient coding hypothesis in neuroscience, which is the understanding that neural circuits are in some sense efficient, in particular metabolically efficient. And what does that even mean? And does that mean in particular that neurons obsess over approaching Shannon capacity, which is a message that sometimes has been taken within neuroscience. Then I'll talk about some of the open issues which are key puzzles in network information theory that are needed in order to understand energy efficient networks in computation and communication. And then I'll conclude, I'll speculate a little bit, talk about future questions. This is, as I said, an early morning talk. I just came back from India, so it's a late night talk for me. So just make it interactive, ask me a lot of questions so that I keep on track and everybody stays awake as well. Okay, so let's start with a very high level motivation of why we care about energy and information, the intersection of the two. Okay, and this is something I found out about 3 months back, just before I gave a talk, that this is really prompting for a need for an energetic information theory. If you look at the human brain, which really, what is it about? It's about thinking, it's not about really doing stuff, right? It's not about moving around, except for graduate students. It's not really about doing stuff. It's about just neurons communicating with each other and doing some computation. And that in itself consumes 20% of the total energy of a human being, which is a humongous number, right? At least I think so. And if you look at computing and communications in the rest of the world, the electricity, 8% of the electricity in the world in 2011 was consumed by information and communication technologies. That's not just data centers, it also includes televisions, but in general all kinds of processors and all kinds of communication systems, base stations and such. And it's projected to, it's actually already gone up, and it's projected to increase to 15% by 2020. So it's becoming comparable to the brain energy, which is again a bit of a surprise to me, and an intriguing surprise, but that's that. So it just brings out the problem, the importance of the problem just from a whole world energy perspective, that we need to care about energy of communication and computing. But even from a limited perspective of battery limited devices, everybody cares about battery of cell phones. When you download data, it still consumes energy, a lot of energy. And for short distance wireless communication devices, wearables, brain machine interfaces, whatnot. So that's another motivation for understanding the intersection of energy and information. So since we are Shannon inspired, we have to look at fundamentals here. Let's ask the question of what are the fundamental limits on energy of information transmission, right? How much does it minimally require to communicate information? And Landauer was a physicist. He essentially spent his life looking at this question, and he came up with a surprising answer that might actually surprise information theorists here as well. Does anybody know what an information theory answer is for minimum energy per bit? Is it K something?
Okay.
There's a K in the front. KT log 2. Nobody has. So
you're talking about additive Gaussian noise channel?
Yeah, so that's what, yeah, exactly. So you have to make these assumptions of the additive white Gaussian noise channel, and that's something that I want to bring out in this slide, what those assumptions are. But are people familiar with the KT log 2 result? So let me just understand so that I can pace my talk accordingly. I don't have to run through all these slides at all. But how many people have taken a class in information theory? Okay, it's a little less than half. So I'll talk about information theory results, even the well-known information theory results in reasonable detail so that you get an idea of what's going on. And one of them is just going to show up. But the traditional thinking in information theory is that, okay, channels are Gaussian, so there is a certain minimum amount of energy required. And Landauer was actually very annoyed by that. So in 96, he came up with a limit in 61 on the energy of computing. And then 96, he wrote a paper, which is Minimal Energy Requirements in Communication, where he emphasizes there is no unavoidable minimum energy requirement per transmitted bit. Okay, it's 0. And why did he say so? So there were 2 reasons why he said so. One, he's a physicist, and physicists, if you remember from your high school lectures, right, they like to assume things are frictionless. It's idealistic assumptions. So literally, he actually said this scheme assumes, he gave a scheme in the paper where he says this scheme assumes that friction and noise can be made as small as you want. They can be completely eliminated. And the reason is friction is a dependent force. Is that it's not, if there's a single atom, there is no friction, right? There have to be entities that collide against each other. So That's the physicist viewpoint, right? When they think of fundamental limits, they think of fundamental limits that don't depend on what system you're implementing it, as long as they're only limited by laws of physics. And here's where I bring in Shannon's viewpoint, which is a very engineering viewpoint, where this is the famous expression. I'm sure people have seen this one, right? Everybody must have seen this one by now, which is capacity is W, which is bandwidth log of 1 plus SNR, right? And the stark difference shows up right here. So this is SNR, you transmit with certain transient power, and there is a path loss coefficient that shows up here, which is eta. So this path loss, you can interpret this as friction, right, which is something that physicists are ignoring, because the farther you communicate, the more loss in energy you have. And there is an explicit noise term here, right? So Shannon is saying, look, friction and noise are realities of life, let's take them into account, and then let's ask the question of what is the maximum rate you can communicate across the channel while driving the error probability to 0, and surprisingly, amazingly, it turns out to be non-zero for many channels of interest, and it's given by this quantity. So I'll go over this expression again. But that I think is a fundamental difference between the approach that physicists take and engineers take, and we very much are going to take here the engineering approach to the problem of energy minimization. So let's see how we take that. But before we get to that, I want to explain Shannon's result in a bit more detail, especially because not everybody is initiated to information theory, or at least hasn't taken a class in information theory. And I want to introduce the central result in information theory by a very classical analogy. Some people might have seen this earlier. But let's say a teacher wants to give a talk to a certain set of students in a class, and the teacher is not loud enough. By the way, am I loud enough at the back, Mohan? Okay. So if people at the back can't hear, right, then reliably, of course, right? Shannon wants everything to happen at ultimate reliability, error probability going to 0. So if people can't hear, then the two options that the teacher really has naturally is either to speak slower, which is to say, repeat herself, right, or speak louder, shout. Right? These are the two natural options. Shannon says actually none of these is required, and he proposed a solution, which sounds really weird. He says that the teacher must have a very long lecture to give, a lot to say, right, a whole book to communicate, and then append some extra information at the end, which is parity bits, right? And essentially, so append some information which is a constant fraction of the information that you have to communicate, mix around this information, okay, very nicely. And this is still mysterious, right? And then if you do that, then you get this magical plot, which is called the Shannon waterfall plot, which says that even as the error probability is going to 0, you can whisper. You can communicate with bounded transmit power, right? So that's a very counterintuitive result. And of course, the way we understand today that this is happening is really that this coding strategy becomes more and more complicated. In effect, you have to take longer and longer block lengths, so the n is going to infinity. But really, block length is still a mysterious concept, right? What is the interestingness in block length which makes this happen? So that's something also we are going to come to. Okay. So what I want to bring out here is this is figure 1 from Shannon's paper. And what I'm trying to say is that there is something that Shannon deliberately ignored, which she could because of the systems he was interested in, but we can't ignore today. And that is the energy required in processing at the transmitter and the receiver. And I built out neurons here, but you can very well have circuits here. So there is, and I'll come to the neuronal interpretation a little bit later in the talk, but really if you're thinking of a short distance communication system, there is energy required at the transmitting and receiving end, not just in the transmission itself, of course, right? Circuitry requires energy. And as you use these more and more complicated strategies that Shannon proposed to use, more and more energy is required at the transmitter and receiver. This is an empirical observation that we even tested it using experiments that I'll come to in a minute, but in a very particular way. But this has been known for a long time. And for data center links, for instance, or indoor communications, the energy required in circuitry is actually can be an order of magnitude larger. So to give you numbers, if you want to communicate 5 meters in a data center link or indoor communications, the typical transmit energy is 10 milliwatts, sometimes 30 milliwatts for gigahertz of bandwidth, for gigabits per second of communication. But the required circuit energy can be easily watts, but certainly hundreds of milliwatts. It's just the decoder that is required to unmix the information that Shannon used to code. Okay, so there's certainly something interesting going on here, and my point is that Shannon deliberately ignored this, and he could because he was interested in long-distance communications. This is in 1948. This is the beginning of space age, really, right? Sputnik 1 had just been launched. People were thinking of telephone, television, telegraph, and I like to cite these examples because all of these have the word tele in them, which really means in Greek far off. So people were thinking of long-distance communications, where this energy really didn't matter. But if you're thinking of applying information theory to circuits, to neuroscience, to short-distance communications, we really have to take this into account before we can apply results. We need to be sure that those results actually apply even with these energy costs taken into account. So we need to be careful about that. Okay, so let's begin to think, how do we even take this into account? What is the minimal total energy required for communications? Let's begin to ask this question. Let's first try to understand what the crude answer could look like. Okay, so we saw that for Shannon, you can just whisper, even as the error probability here is going to 0, you can transmit at a bounded transmit power, and you can communicate, right? Which is a surprising and interesting result. The natural question becomes, if you take into account the energy at the transmitting and receiving end, then does the total power remain bounded, or does it become unbounded? And if it becomes unbounded, that this is an intellectually interesting change that has happened, because then we have to be careful about applying the idea of capacity to short distance communication and computation systems.
So, Pulkit, sorry, are you kind of assuming a quote-unquote separation theorem in that so you have your message, say it's in bits,
yeah.
Then you have to pre-process this message to represent it, and then you have the fundamental modulation scheme that ultimately is dumping the energy into the antenna.
Yes.
You sort of have these two modules. And
yes.
Analogously, at the receiving end, you have
a demodulation
module that's kind of doing the standard analog circuit things that we don't learn.
Yes.
And then secondly, you have your module that is sort of processing those bits and doing inference. So I almost hear, like in your talk, are you assuming some type of separation theorem where you have the energy that inherently represents the signal electromagnetically, but before that you have the processing to put redundancy in the message, and analogously two different modules, one of the kind of the physics and the analog circuits, and then secondly the one that's inference. Is that kind of implicit in what you're saying? Or?
It is actually implicit. Let me think if we can actually go beyond that. The question makes sense even beyond that. If you have bits to communicate, right, what does total energy look like? But the results I have actually do assume that there is a certain separation. There's a certain model of modulation that I'll use, which is actually a binary model.
Okay.
Okay. So does the total power behavior still remain bounded, or does it go unbounded as the error probability goes to 0? This is the crudest question you can ask. And let's see, how do we begin to answer this? So coming from a theory background, I really wasn't very inclined to do that, but I was forced to, in this case, actually work with people who actually build things. So I got an undergraduate student who was a CSoI member as well. We had a joint grant, and he used to be a student at Berkeley, Karthik Ganeshan. Now he's a student at Stanford with Subhashish Mitra. So also looking at still issues between circuits and information theory. And this undergraduate student, what he did was he said, let's try to first understand this from brute force simulations. So let's build circuits, let's build circuit models in the right circuit software. This is, I think, the XSpice is what was used for post layout power calculations. And then let's calculate total power consumption. So this includes transmit plus decoding power. And for what it's worth, it does seem to increase as the error probability goes to 0. Now I should mention this is after optimizing over 4 different classes of codes with different girths. So overall I think it's about 100 different classes of codes. This is like girth 6 and 10, girth 6 and 10, and so on. So these are multiple decoders that they optimized over, that he optimized over. But really it's by no means exhaustive. This is just LDPC codes for those who are familiar with what those things are. But it suggests a hint. It says that the total power increases to infinity. These inflection points are where the optimizing code itself changes. So it goes from one LDPC to another. And then you have this, this is the optimizing transmit power, and this is the total power that you're trying to minimize. So that's what the total power curve looks like. But of course, this is by no means something to be very happy about. This is an undergraduate student working for 6 months on, actually 1.5 years, on a simulation and coming up with these numbers. But this is by no means fundamental. I mean, I think this was very cool work, but this is by no means fundamental. So this motivated us to study models, and this is again where I want to bring out the Shannon approach to looking at problems vis-a-vis the physics approach to looking at problems, and really the engineering versus the physics approach. So Shannon explicitly modeled channels through which you communicate, and in the process using them to arrive at his fundamental results on capacity. So really what we should do is we should have models of implementations, models of circuits, right? Which can, so for channels we have the BSC, we have the AWG, and we have the BEC, we have various channel models. We need similar models for implementation, right? Maybe multiple models that can capture the power required in the circuitry, in the encoding and decoding and perhaps beyond. And these models actually exist. People have thought about these things a lot. But what we want is we need models that just as Shannon had, which are both relevant and analyzable. This is a sweet spot that we want to hit, that they should somehow capture the physical energy being consumed and yet have the simplicity to them so that you can actually throw your analysis at them and understand what the requirements on the energy are. And that's a delicate balancing act. I have to admit that so far our results are really leaning towards analyzable, though every once in a while through some band-aid patch-ups, we try to get to relevant results as well, and that is in collaboration with experimentalists. Okay, so what I'm going to present here is the simplest model that we have so far. We have more complicated models for which we did analysis as well, but this is what I call the wire-free model that we have, and this is the most recent model. It's convenient to present results in this model in talks. The model is very simple. This is a model of computation. So think of this as the circuit at the transmitter and the receiver. It has some, sorry for these small nodes, but it has some, it is basically a substrate, circuit substrate in 2 dimensions. 2 dimensions is not necessarily a requirement, it can be a 3D circuit as well. You have certain nodes that are the input nodes, where the input of the computation arrives. You have certain nodes where the output of the computation will eventually be stored, and then you have some communication that happens between these input nodes, some helper nodes and output nodes, and at some point, right, the output of computation is stored at the output nodes. There is a major restriction of this model which I really, really want to relax, and if somebody is interested, especially all the CMU students here, I would really want to relax the 2 of them really. I would really want to relax the fixed schedule of messages. I just came from India. So fixed schedule of messages is something of a constraint here, by which I mean that the input arrives at input nodes, and then you know, regardless of what the input of the computation is, which node is going to pass message to which other node. Okay, so which green node is going to send message to which black node, and in the process, and eventually arriving at red nodes. Think of the FFT butterfly circuit. That's a very specific order of messages, right, that you pass. There are stages to that message passing. But really, this is not all the freedom that is available in circuits, in biological or electronic circuits, and we need to go beyond this. But right now, this is a restriction.
In some sense imply there's an underlying clock governing, the
So,
synchronization amongst these guys?
Not necessarily. So there can be asynchronicity to it. Actually, yeah, no, you are right. So there is an underlying clock to it, but it's not necessary that all the nodes communicate to everybody else in each clock cycle, which is a relaxation that we have from a previous model that is being used widely in circuits literature. Okay. In theoretical circuits literature, really coming from computer science community. And I'll talk about it too at some point if we have the time. So now we need a model of energy consumption on this model of circuit, right? Does the circuit model make sense so far? Okay, very simple, right? A circuit is a bunch of nodes that are connected using communication links. And here, there are no wires. It could be a wireless model, or really wires are just absorbed and not explicitly brought out. And there is a minimum distance between these computational nodes. That's some lambda. That's really, if you're familiar with circuits that talk about 22 nanometer, 45 nanometer, think of this as the distance between, I mean, it's not entirely true, but think of this as the distance that technology specifies. It's approximately true. And yeah, okay. So now I want to put an energy model on the circuit model, and the energy model that I'm going to impose is what I call the information friction model, which I draw this analogy with the Newtonian friction model just for fun, but I'll explain why this is a somewhat serious model as well. So the information friction model says that the energy required for communication on these links in the circuit is proportional. First let's talk about the Newtonian friction. If you have a weight that you're dragging along a surface, the energy required to drag that weight is proportional to the weight of the object times the distance to which you drag it, right? Just Newtonian friction. Similarly, you can define information friction just for fun if you like, that the energy required for information friction is the number of bits that you want to transport on a link on the circuit times the distance to which that link drags that information to, multiplied by a coefficient of friction, which is a coefficient of information friction. Okay, but actually, let me see how much time I can delve on this for. How much time do I have, Todd? I don't know when we started. It's 9:33.
Keep going.
Okay. Okay. So just to explain the applications, I misplaced my pointer. Yeah. So where is the inspiration coming from? And the inspiration initially really came from actual silicon circuits, because the wires that connect transistors on these circuits, the resistance and capacitance of these wires grows linearly with the length of the wire. So the more times you charge and discharge it, you pay the energy, which is half CV squared, and C is linear with the length, so you pay energy which is proportional to the length, the distance, and the more times you charge and discharge it, the more bits you communicate, so there's where the B comes from, right? It's again a technology limited thing, so the particular circuit technology of course uses binary transmissions. You could use QPSK transmissions on circuits if you like, not 4 levels or 3 levels or something, right? But you would still get some different coefficient of friction, but effectively you'll be limited by something like this. So it applies to circuits. My contention is, and I would be willing to argue, but let's do that after the talk, is that it applies to neural signaling as well. And the reason being that neurons, when they're connected with an axon, the axon has nodes of Ranvier on it, which essentially boosts the signal every time you go a certain distance. And so the energy consumption, this is like repeaters, right? And if you put regular repeaters at regular distances, then the energy consumption will increase linearly with the distance as well. This is a crude approximation, but I'm really going for lower bounds here. So when axons become longer, they also become thicker, which requires more than linear energy. But it's a lower bound and a crude approximation. Optical fibers, carbon nanotubes, and even if you want to ship information by burying it in a memory, then the weight of a memory cell really, this brings together these two models, because as the weight of a memory cell increases, your energy requirement also increases, and also the number of bits increase. Okay. So that's the motivation for this information friction model, and this is our model of implementation. Now we want to use this to understand the energy required at the transmitting and receiving ends of a communication system. Okay, so let me first give you the results, and then I'll get to how do we even get around to saying something like this. So the result is that the encoding and decoding energy is lower bounded by this quantity. K is the number of bits you're trying to communicate across the channel, so really ignore this if you're interested in just per bit energy. And then there is this expression which is square root of log of 1 over PE divided by the transmit power. So what this is saying is, if you speak louder and louder, if your transmit power increases, then the encoding and decoding energy reduces, which makes sense, right? If you shout, if you do uncoded transmission, which really is PT equals log of 1 over PE, and here's where I realized that I've forgotten to tell you something, so let me tell you that first. There is an implicit model of the channel. It's actually an explicit model of the channel, and the channel is assumed to be a binary symmetric channel, our favorite channel really, bit flipping channel, with the additional requirement that the bit flipping probability P is related to the energy consumption. Let me write it here. So it's a BSCP, but P is e to the power minus some constant times the transmit power. And this is really coming from AWGN channel. So your favorite Gaussian channel with your favorite binary signaling really gives you this at high SNR. So that's what I'm using for simplicity. Okay, I'll see if I need to lower this again. I think I'll need to. Okay. It doesn't want to stay down there. Okay. So that's the model. So if your transmit power is actually log of 1 over PE, then you require no encoding and decoding energy. So this bound just becomes a constant, and that's when uncoded transmission happens. But if transmit power is anything lower, then you actually have to pay encoding and decoding energy, and the lower the transmit power is, the more you have to pay. Okay. There is another stronger result that we have that I'll get to in a minute. And what this means, it means a couple things. One is that if you do plot total energy as the error probability goes to 0, it doesn't remain bounded. It actually goes unbounded in this model of implementation and energy consumption as a cube root of log of 1 over PE. So it's not whispering. Of course, you can still whisper. You can transmit with bounded transient power. But if you do that, so here what I'm trying to do is I'm trying to say you have transient power plus this power. You try to minimize that. If you just transmit with bounded transient power, if you whisper, then your total power is actually larger. It's a square root of log of 1 over PE. All I'm saying is this PD is a constant, so you get a square root. And which is why the optimizing transient power turns out to be a cube root of log of 1 over PE as well.
Can you separate that in terms of encoder power,
Yeah.
and encoder energy and decoder energy? Is the dominant term the decoder energy? Or?
So far, the bounds are the same for both.
Okay.
I don't even know if there is a trade-off between the two. I have not been able to establish that. Okay. But practically, we know that for some codes, like LDPC codes, encoding energy is actually larger. For many other codes, decoding energy is larger in order sense. I think it depends on the particular code. So for LDPCs, I'm saying that really for encoding, the best algorithm that they know is almost linear, but there is an order n squared term which is tiny.
Okay.
That's what I'm basing it on. But for various codes, people have figured out that actually encoding energy in order sense is larger. For most practical implementations, they choose codes for which the encoding energy is lower than the decoding energy, and decoding energy becomes the constraint, which is why there are many more PhD theses on what is the best decoder for this particular code which is used in this standard. This is, by the way, an active research area in circuits, or at least used to be 3 or 4 years back.
I think it's interesting. I mean, from a total theoretical perspective, Dave Forney told us that if you take a random linear encoder, it's going to work well.
Yeah.
But maximum likely decoding over linear codes is NP hard.
Yeah.
So very traditional theory suggests that encoding is easy, decoding is hard. But what I hear you saying is that when you really look at the details of the circuits, the opposite is true. The encoding is eating up all the energy, and the decoding is.
No, I don't really know which one is true. Okay. So the lower bounds turn out to be the same. Okay. And these lower bounds, I should say, they have this qualification that everything is done in parallel, right? And of course, the model constraints that I put, right? All of those constraints are valid. I just want to finish one thought. So there are those additional constraints. For most practical codes that I know of and practical implementations that I know of, there are very few papers on encoder implementation. There are papers out there. Most papers do focus on decoders. So I think they choose codes carefully enough that decoding energy matters more. And really, this change has happened. What you're talking about really happened with modern coding theory, because our decoding algorithms became linear time, right? And parallelized. So now it's a bit of a question. 20 years back, nobody cared, I'm sure. Sorry.
I had a question which I think is related. So is there a way of relating fundamentally the complexity of an encoding scheme to the energy consumed?
Very nice, yeah.
Does it require an implementation model, and
very nice.
Unless you have it, you cannot bring it to the same.
So the complexity, you're saying Turing complexity, right? Essentially, which is a model as well, right? And I deliberately stayed away from the Turing machine model. Right? This is a model for complexity too, if you like. This is what I call the bit meters model of complexity. And this is really coming from what is called the 80 squared complexity that I didn't even get into, which is the area time trade-offs that people studied in 1980s, which is called VLSI complexity. So these are just different notions of complexity. It's by Clark Thompson was the guy who started the whole idea, but a lot of discussions happened. Abbas El-Gamal was involved in development of the theory, and I'll talk about one of his results as well. So this is just another notion of complexity. I stayed away from Turing machine complexity for 2 reasons. The more interesting reason is that it's less practical because it lives in this infinite dimensional space. And really, computer scientists don't limit themselves by physical laws. They limit themselves by laws of logic. But I wanted something that is more physical, that has something to do explicitly with energy consumption, and so circuit models make more sense there. The other thing is, and really what happened is in our simulations, we found that wires consume much more energy than nodes, and Turing machine will only capture nodes. So we have to capture wires in order to get to these results, which is why information friction is really about moving information. So that was one reason. The other reason is Turing machine model is ridiculously hard to analyze. We still don't know if P equals NP because we cannot derive lower bounds that are exponential for exponentially hard problems. So getting lower bounds there is just something I didn't want to get into. Yeah. Okay. So In comparison, so these are the results for total power consumption. Lower bounds, the upper bounds, that one simple upper bound is uncoded transmission, and that gets us log of 1 over PE within this model, which is much larger. So at least even with this revised model, there is benefit to coding, or potential benefit to coding, because the lower bound is significantly lower in order sense than the upper bound, than the uncoded transmission upper bound. And then actually we have upper bounds for LDPC code as well, codes using LDPC codes, and they sit at square root of log of 1 over PE with total power optimization, just to complete the story to the extent to which we have it right now. Okay, so what's the key idea? And I want to explain that. And yeah, okay. So the key idea is, now remember in the Shannon whispering strategy, the transient power remains bounded even as the error probability goes to 0. But it requires the block length to go to infinity, and you need these larger and larger block lengths, and you need to mix this information, and then you attain this this really nice strategy. So what would happen if you had a circuit and you did not spend a lot of information friction energy in this circuit? What that means is that there is not a lot of movement of information on this circuit. So what I'm going to do is I'm going to split this circuit into two pieces. And then I'm going to ask the designer, hey, is there an information flow between the upper and the lower part of the circuit? Okay. And let's say the designer takes the extreme view and says, no, there is no information flow between these two parts. Then what's really going on is that the upper part is limited by the block length, which is generated by these. There's a function, right? So let's say this is the decoder. So this is the input nodes. Input nodes are what receive the channel outputs. So these are the channel outputs. The decoding of these 2 bits up here is limited by whatever these channel outputs are, right? You have no interaction with the other channel outputs. So effectively, you are not exploiting the advantage of long block lengths that you had, just because you broke the code at the decoder in 2 pieces, right? Effectively, that's what you did. Does that make sense? I can go over this again, but this is the one sort of one technical point in the talk.
So you're assuming that the top and the bottom parts don't interact, right?
At all.
Okay.
That's the extreme situation. And in that case, you are limited by the block length of the top part and the bottom part, and that limits your error probability, right? Now the key is, of course, if there's a little bit of interaction, right, not significant interaction, then you still need to be able to get a lower bound on the error probability. That's where a little bit of technical stuff is required, where we use ideas from sphere packing bounds. In fact, to make them simple, we use sphere packing bounds at rate 0, but you can actually tighten them and use non-zero rate sphere packing bounds as well. Okay. So this is still, what this is saying is, okay, the error probability was decaying is exponentially in n, which is how it decays. If you had the full block length, now it's decaying with exponentially in n over 2. It's still exponential, right? It doesn't make a whole lot of difference. So what you need to do is you need to break the circuit into many, many, many pieces. And that's what we do. So that's getting into a bit more of a detail of the technique. And then we want to capture bit meters, not just number of bits. So we not only break it into multiple pieces, we break it into inner and outer squares and create some distances between them and force the designer to declare that, okay, if you have a certain error probability that you're targeting, then if you don't have enough communication on the circuit, then I'll prove that you are not achieving that error probability. So proof by contradiction. So you require a certain number of bit meters, and that really is what yields a result. This really, so this I should mention here. So these models are coming from Thomson's models in 1980s, and which are coming from Carver and Mead's models in 70s, or discussions in 70s. Al-Gamal actually worked in this area, and 1984 he had a result which was about encoding and decoding area times time squared complexity. And that used very similar techniques as well, which is something I rediscovered, or I discovered that, I didn't rediscover the result itself, I discovered that paper in this one conference proceedings, and I went and spoke to him about it, and he had forgotten about the result. Then we had some follow-up results on it, which I'll talk about briefly, which make this make this understanding a little bit more refined as well. Okay, but all of these results are really about using informational constraints on computing. So computing is not just limited by number of operations; it's limited by flow of information, right? And this is perhaps broadly applicable beyond circuits as well.
So to make sure I understand, the blue dots are the input signals, and the red dots are kind of the reproduction.
Yes.
Reproduction bits. And the key idea is that if you go back to your previous, the first one was just the top and the bottom. Right, so what I thought I heard you say was that you could have all of those guys interact, all 5 of the blues
Yeah.
interact to give rise to the
To the
5
red ones.
outputs.
Yeah.
But if you do that, you consume too much energy.
Yeah.
Ideally, because the bottom left has to talk to the top right,
Yeah.
and it goes over a long
Yeah.
distance, you consume a lot of energy.
Yeah.
So instead, what you do is if you know that you only care about error probability of being 0.1, let's say,
Yeah.
then you don't necessarily need to go all the way from the bottom left to the top right,
Yeah.
because you're consuming too much energy. So then if you go to the next slide, I just want to make sure I understand. When you drew those squares, each one of those squares either only has red or only has blue.
Oh yeah, sorry.
So I just want to make sure I understand.
I'm putting no constraint on how many blue or red are in there. But what I want to capture is how many reds, how many outputs are in there.
Okay.
And enough information needs to flow into those red ones.
Okay.
Yeah. So this is a visual approximation, really. Okay. So then we tested this one bit. I forgot something. But anyhow, we tested this one crude highest order bit of this work, that if you transmit with bounded transient power, then the required energy is much larger experimentally. And for the 4 codes that the student had simulated, he found out that the total energy was actually indeed much larger than if you optimize over transmit and decoding energy in this case. Okay, I want to end this discussion. How much time can I take?
Brent is the gatekeeper.
All right, yeah, I think
Ouch.
we got a little bit of a late start. How about if we try to finish by 10 after
10 after 10.
So that would be
That's very nice. So I have 20 minutes then. Okay. So I'll try to finish in 15 minutes so that we have 5 minutes of questions. Okay. So 2 more results, but I really want to talk about only the first one because it brings out something that I haven't talked about yet. This is a result for node models where only computations consume energy, but under this circuit model of implementation still. So what happens is, in order to communicate to more, and this model has more constraints on it. You can communicate only in clock cycles and only to, in each clock cycle you have to communicate to everybody that you're connected to. And there is a bounded degree constraint, which is this alpha constraint that shows up. But the interestingness of this result is that as the gap from capacity goes to 0, so this is capacity minus rate, the number of clock cycles at the decoder blows up to infinity. So the decoder has to work harder and harder. And this is a result we don't have for the encoder. This V of PD is, by the way, the dispersion thing that Yuri Polyansky and Sergio Verdu have worked a lot on recently. And this really comes from because we are driving closer and closer to capacity, just as the question that they're interested in. And then really, what is the cost of decoding, right? That's there it's a block length answer, here it turns out to be an energy answer. And really it happens because as you dedicate more and more clock cycles, you can increase your neighborhood size, the number of nodes each node is talking to, which as it turns out is needed. You cannot have local neighborhoods in the code without making it not good in error probability sense. Okay, so that's just to summarize the understanding that we have. Now I want to shift gears a little bit and talk about what is called the efficient coding hypothesis in neuroscience, and then just touch briefly upon how it is often tested and how we need to be careful about that. And really the central question is, do neurons obsess over approaching Shannon capacity, which by now you would have gotten a flavor that our answer is going to be no, they don't really obsess over approaching Shannon capacity, probably in any sense of the term. But let's get to it gradually. So these are 3 statements I took for the efficient coding hypothesis. This is the original paper, which is actually a very nice read, even a bedtime read if you're interested, by Barlow in 1961. Where he says, and his hypothesis was more limited in spirit. He said that sensory relays really re-encodes messages, but his emphasis was on compression. So the natural images that you see, the body gets used to them evolutionarily or through development, and really codes information that is the most relevant by taking the statistics of the underlying source into account. So that's what he wanted to say. He retracted it partially in a 2001 paper. But I think in the core of it, he believes that that's something that is being done. His model was also noiseless. Bialik has studied more noisy models where he says that what many parts of the brain are doing is that they're trying to maximize the information communicated, and he uses a lot of ideas from mutual information to characterize how much information is being communicated. There's a lot of work by Vijay Balasubramaniam also about it, and he also talks about given the physical constraints. There are explicitly energy constraints as metabolic costs that have shown up within the work in this direction. And really the question I'm asking is, what can we say using this understanding that we have about total energy consumption in communications on to this? Can we shed any light about this, or can we begin to ask some questions here? And really this is the beginning of asking questions in this direction. So the first thing that I have to acknowledge is that there are many differences in models, and these are the ones that I could pick out, and I'm sure there are many more. So the key differences between circuit models and neuronal models is that neuronal computing, and sorry, not circuit models, but the results that I have presented so far and the neuronal models is that neuronal computation is very interactive and also noisy. And so far my computation is completely noise free and not interactive in that the encoder doesn't interact with the decoder. There is no feedback. So this is something we were able to relax recently. So this is something we can take care of. The other is neurons differ in sizes and metabolic potentials as well. The axons can be larger or smaller. There can be more myelination or less myelination. That makes noises different, that makes energy consumption different. So all of that needs to be taken into account. There is 2D versus 3D as well, but that's a minor difference that can be easily taken into account. I think one of the bigger things is BSC is a terrible model for neuron-to-neuron communication. And this is something I have a very partial relaxation where I can consider Poissons instead of BSCs, not worth getting into right now. And then I think, let me bring this problem out a bit more explicitly. I want to say that the order of messages cannot be fixed in advance if we want fundamental results in this direction. I think that's a relaxation of the model that is needed, because if you think about it, if you can detect in some local neighborhood that there is some atypicality that is happening, right, you can ask for more messages, which is the typical way in which we use feedback in communication systems. So I really need to take into account this as well, which is something I don't know yet how to. But so let me just give one highest order bit of the result here. The result is about noisy computing, again using a BSC style of model with noise between nodes. And what I say is, let's assume that there is a noisy cut, effectively, that separates the source nodes and the output nodes. So this is the input of computation, think of a Fourier transform, and this is the output of computation. And there's a noisy cut that separates, which means that all the messages that travel over this cut have some noise, which is really a function of what is the energy you're dedicating to the link across this cut. And it goes as a BSC, again going down exponentially in the energy. This can again be relaxed, at least a little bit. And again, the order of messages is predetermined. So if I do that, then again a similar result falls out, except with the sophistication that now you have to take this feedback link into account. Again, the feedback is noisy, which is what we fundamentally rely on. Otherwise, the result would be, I think, 0. The energy required will be a constant. You won't get any expression. But we make use of the fact that this interaction is also noisy across the noisy cut, and that's how we get this result. But this also means, in effect, that and people have been asking this question in different formulations, that what is the Shannon capacity of noisy computing, and how do we even begin to formulate this question? But really, if we take an energy viewpoint on this question, and if we believe in BSC models, forget for a moment neural computing, then the Shannon capacity is 0, because you cannot have bounded energy per bit as the error probability is going to 0. The total energy per bit is going to go unbounded. Okay, so there is some resolution to these two. I don't have a very good result here yet, and if somebody is interested from the neuroscience side, I would be very interested in talking to them about. I have a partial result for firing rate on how to derive lower bounds on energy consumption with firing rate models of neuron-to-neuron communication, but even that is limited. So I really want to deepen this, and then this one I have no idea of how to deepen this yet. Okay, so I'm going to start wrapping up. So two of the key puzzles that I think from this kind of an understanding that we have converged to, two key things that we still need to understand when we think about studying computational and communication networks that we don't yet within information theory are friction and noise. By friction, I again mean something which is about losses as the distance increases. And this is something, there is a better handle that we have on this, mostly owing to the VLSI theory that existed and still does in 1980s, and that really comes from a computer science background where they took explicit wire lengths into account. So there is, it's not a very good understanding of energy consumption, it's better associated with wire lengths than energy, but it's a good starting point in that direction. What is, however, very weakly understood, I think, in information theory is noise. And this is the reason I believe we need a stronger understanding here. What we don't know is, for instance, if I have a set of nodes, if I have a network, right, we talk about relay networks in information theory. If every link is constrained to be scalar, okay, so you're not allowed to use the block lengths that we use commonly in information theory, then you can imagine there is no way to get rid of errors, right? So simple thing, let's consider a line network, node after node after node, each connected through a BSC. The best thing you can do is repeat the bit, right? That's probably the only thing you can do. I don't know what the best thing you can do is. But if you use a cut set bound, then you're going to just use the weakest link, and that's all you will get. The number of links as it increases, you will not be able to demonstrate that the error probability is increasing. There are tools in information theory that actually get us there. So error propagation to that degree for a particular line network is understood using Evans and Schulman, and recent work by Wu and Polyansky that came out this year, and Sudeep Kamat's work with Anantram Nair and Gohari that came out last year. They're beginning to address how the information decays as you go down a noisy path. But I think this understanding is still very weak in order to put together something like how do you build a noisy FFT, right? And this is the question that I'm really motivated by. How do you build an FFT computation with noise? And one of the things that we have tried this year is doing an encoding with noise, and that seems to succeed to a certain degree. So we can control error propagations there. Though we don't have a good fundamental understanding of it, we do have a good strategy to see how that happens. But I think eventually, to put all of this understanding together, we need to put friction and noise in one system and understand energy consumption while there is noise. And that's a question that I think is broad and open even for simple examples, and I don't know how to address that yet. Okay, so to conclude, and I'm going to end with a speculation after this slide. So this is not the last slide, just to warn you. So to conclude, we talked about an energetic information theory, which is to say that take into account energy in all components of the system, and it turns out that the results are counterintuitive, slightly counterintuitive from a traditional Shannon theoretic viewpoint, but of course the model is different. We are taking total energy into account and it increases to infinity. You don't want to communicate close to Shannon capacity, you get results of this nature. But again, you shouldn't have expected Shannon style benefits for these problems anyway, because we are taking into account more energy. So it's not all that surprising at the end of the day. And this is still, I think it's a speculation because I don't have the core result, that if we are thinking of biological cells and neurons, we shouldn't think that they are trying to optimize capacity. Even if you believe in the efficient coding hypothesis, that we are doing things efficiently, it's not necessary that that neurons are doing things efficiently using the capacity limit. And where this makes a difference, let me talk about this point first. Where this makes a difference is when you try to use the estimation of an input distribution to say that neurons are communicating at capacity. I think that twist means that neurons are obsessively trying to optimize the capacity of the computational communication system, when it's not the thing to do when you optimize all the resources in the problem, in particular energy, but also wiring, if you like. But I think even if that's not reasonable, what is still reasonable is to use mutual information as a metric to understand how fast the computation is happening. And this goes into deeper ideas, which is really about how fast you can achieve the distortion rate bounds, not error probability going to 0. So I think we shouldn't think that neurons are, I don't think anybody believes that neurons are communicating with error probability going to 0, but they're communicating within some distortion. And if you take that approach, then mutual information is still a pretty good metric, because you attain the right distortions with mutual information, which can be actually not very close to the capacity at all, or it's not obsessively close to the capacity, if you like, as is demonstrated by Gaussian D of R bounds, even for the scalar value, which is something I can get into in detail in questions if people like. So yeah, I think that's my speculation, that this could still be a good metric, but looking at input distributions is not a good idea. And then some of the ongoing work, we are looking at approaches to reduce energy consumption, especially in brain-machine interfaces, but in computation and communication systems in general. One of the things that we have started looking at is, if you don't need to communicate the whole message, but just communicate the relevant pieces of the data, suppose you have a lot of data to communicate, how would you do that? And that brings together machine learning and information theory, which is a work that we have recently submitted. We have discovered some trade-offs between information frictional energy and speed. So the faster you want to compute, the more energy you have to expend. And that fundamentally shows out in this model, which I think is interesting. Then I already talked about error control, or not letting the errors propagate in encoding, and that's one of the things that we are looking at. We are looking at brain-machine interfaces, something I already mentioned, and I think this issue is something I want to get to, which is flexible schedule computing as well. Okay, that's all I have. Thank you.
All right, we can take a couple questions. Yes, sir.
So for neurons, there is one aspect of specificity. There is a receptor that is specific to the ligand that binds to it. How does that really figure into the energy consumption, as well as how that will conserve the energy?
So the way I'm thinking of it,
when you compare with the circuits.
it's the energy required for transmitting the spike that I'm thinking of. And so, Todd, if you would like to come in, that's, but this is the model that I'm thinking about. So you have a neuron. Ouch. And it has a certain axon, and the axon gets longer and longer. So there is some myelination here, a myelin layer here, and then in between there are nodes of Ranvier which actually boost, where there's no fat layer, which boost the energy of the signal over and over again. So what I'm accounting for, so I'm ignoring some of the energy consumed in this system altogether. I'm focusing on the communication energy, and I'm saying the farther you have to transmit the signal, the more such repeaters you will need. And if you can account for the cost of one repeater, then you can translate that and the distance that it communicates to. You can translate that into a coefficient of information friction. And then you can hopefully use the technology. Of course, I still have spiking model kinds of things I don't understand how to build into this technology, in this technique yet. But does that?
Well, so there is, I'm talking about something that happens in the memory. I'm not expert in information.
Yeah, sure.
I'm a biologist. I'm thinking from a biological perspective. You have specificity at the surface, and then you have many molecules that are also very specific. There's change in conformation, and the transfer of information that occurs inside the cell.
Okay.
These are very specific.
Yeah.
There's a very high level of specificity to that. So I wonder whether that specificity drives and minimizes the energy constraint.
Interesting.
So even though it's a long distance, but there's a lot of messages, information is being transferred from one molecule to another, either in a linear way, there's a network, they're communicating with each other. So, and I was wondering whether, is that what you were thinking of noise in the cell?
Okay.
Because specificity will minimize the noise as well, because it's very specific in one direction. So the other thing is that there are many things that happen on the surface. It's really converging into one set of signals that are being transferred. So there are lots of information that's merging into, it's a conduit into one transcription factor or one neurotransmitter that's affecting communication. Right? That's being, I don't know, I mean, I know that the neurobiologists here too.
I think the punchline is that there's a lot of sensitivity, there's a lot of specificity, things that happen at the molecular level, talking about transcription and whatnot, that complement the standard action potential perspective, right?
Yeah.
Right. Is that safe to say?
Yeah.
Right.
I suppose then this is a very action potential perspective. I'm looking at it from a much more crude level, quite literally, in that I'm thinking of neurons as entities, not really thinking of molecules yet. For noise, in my imagination, I was thinking of firing rate models where you have a certain lambda parameter that the neuron actually wants to communicate the firing rate. But there is
much action potential, you know, very standard, almost integrated fire,
Yeah.
you know, and variations on that theme, but very much the electrophysiological aspect is what he's focused upon, which we're bringing to attention. Is a lot of interesting variability at the molecular level in genetic circuits.
It's interesting to see you bring in this issue about compartmentalization. I think in the cell also there are compartments. I wonder whether your idea about really breaking that circuit into pieces, whether that maximizes, applies to cell as well, because there's a very organized structural compartmentalization, even though we might think they're all over the place with compartments.
If only we knew any computation that these things are performing. That's my so far issue. So for the retinal networks, we know very well the convolution that they are performing, at least to a good degree, right? The edge detection and such. But for most biological networks, I'm limited by not knowing what the explicit computation is, like what is the input, what is the output, and how are they related to each other, except at a very high level, right? So that I think. So yes, you can compartmentalize movement of ions or molecules inside a cell, but that is to do what? If we can make that rigorous, I think we can begin talking about lower bounds there as well.